news.
How are you?
Good. How are you?
I am good, thank you. I saw your PowerPoint. It was very impressive, and I really like your foray into audio and exploring everything and coming up with your really cool solution. I'm a believer. I haven't heard it, but I'm definitely a believer.
Oh, and what's your name?
I'm Justice Verhagen.
Just.
Just us Verhagen.
Oh, sorry. I'm changing your name from iPhone.
Yeah.
J-U. How do you spell that?
Justus.
Oh,
Just us, and then Verhagen. Verhagen.
okay, cool. All right.
Yeah.
Nice to meet you.
Nice to meet you.
A little housekeeping. Are you recording it, Perry?
Yes, I am.
Okay.
I guess I just need to send you the link when we're done, right?
Okay. That's what I wanted to check. Okay, sounds good.
All right. Well, where shall we begin?
Right. I guess all of us have heard your BAS presentation, and it was very good. And but you've been told that before. So, but we do have questions because we're all dipole fans.
Yeah.
But for example, your comment that the constant directivity was the ideal waveform and stuff like that in question.
Mhm.
The other ones will be on your measurements.
Oh, yeah.
For
Sure.
example, did you use M noise at all in your test?
What was the word you used?
M noise, Meyer
I
sound. Developed some noise, which is better than pink noise for predicting.
No, my frequency response curves I did on fuzz measure, which it's a sine sweep, and it uses some kind of FFT kind of calculation to come up with frequency response curves, phase response curves, impulse, and all that kind of stuff. So I'm not familiar with the other application that you talked about.
If I might interject, this is Leslie Williams.
Hi, Les.
Hi. So like Justice and you, we all made many kinds of speakers and long time, as in decades, users of dipoles. But what Alvin was referring to was only in recent years, like 5 years ago, has there been a standard for saying how loud you can play with inaudible distortion. And in the pro world, that signal that Alvin was referring to gives a process for saying, okay, given this test signal, how loud can you play music? So you had cited 120 dB.
Oh, right.
With inaudible distortion. So the question is, how do you define inaudible distortion? Or did you use a standard signal, for example, M noise?
Oh, okay. Well, I didn't say that it was 120 dB with no audible distortion. That would be a little extreme of a claim, but so for example, somewhere on DIY audio, I think I have some measurements of the live edge dipoles at 90 decibels output, and I ran second and third harmonics, and it was below, I want to say 1.5% down to 100 hertz, and then the distortion went up a little higher than that below those frequencies. I don't. I'd have to go back and look at at my DIY audio post to see how many of those actually have distortion in them. Um, yeah, what were your questions about distortion?
Well, what we found with lots of experiments over the years is with dipoles is choice of drivers and crossover makes an enormous difference in the distortion, even under linear distortions. And when you get into intermodulation distortion, which I personally think is far more audible, uh, those
I
things
agree.
even make more difference. And what we found is that choice of crossover and choice of drivers can have an orders of magnitude difference in that. And so if you had, in your opinion, uh, well, it could be improved, we have found certain things could radically improve that based on the size of the driver.
Mhm.
But some of the things I couldn't tell from your presentation what the drivers were and what the crossovers were.
Oh, okay.
And we've also found that there are some commercial solutions which can be generally used, which I think might apply to your system to make the system even easier for a non-weirdo like Justice or myself to make. So the first step of questions were there specifics that you had in mind as into optimum drivers and crossovers? And we had some suggestions if there were issues there to make it even easier.
Well, the Bitches Brews use SP Acoustics 15 OB 350 woofers. Um, and those are open baffle drivers. You can buy them from Matasound. And they use, and then the mid-range tweeter coax is the 15 CXN88, which is made by BNC. And
Okay.
those are sold by Parts Express. So that's the mid-range and tweeter because it's a coax. And the lower crossover is 100 hertz.
Mhm.
And I showed I showed on my PowerPoint slides. I showed the lower crossover. In fact, I have that here. In fact, let me show you a little detail about that crossover point really quick here. Just a second. So I'm going to share my screen. This is the lower crossover of the Bitches Brews. Um, this is simulated in um, in um, in Vituix CAD,
Mhm.
and this is a schematic of the crossover. This is a passive crossover at that frequency, and this is the voltage at the drive terminals of the speaker. And so you can see the woofers roll off at about 100 and then they drop at 6 dB per octave. And then you can see the mid range drops sharply at about 50 or 60. And it has this depression here, which is it's the impedance curve of the woofer turned upside down, which works very nicely. It does exactly what I want it to do because it's fine for a 15-inch driver to get a strong signal all the way down to 50 or 60 hertz, but below that frequency, it drops like a rock, and that's great. And to do that with only a standard 6 dB filter is really remarkable, and it's because it's a 6 dB filter. Well, the upper crossover is 3K, and uh, this is the curve. Um, these are the acoustic curves of the mid-range without um, uh, the mid-range without the tweeter without the
Right.
mid-range, and then both of them together. And that is a DSP driven crossover at that frequency. So there's an active crossover at 3K and there's a passive crossover at 100.
Okay. Uh, so I recall seeing this curve, and in terms of offering options to end users, one thing immediately thought of is that for many years, and actually now there are many more sources in the pro world, there are packaged EQ, pre and post crossover EQs, linear phase crossovers, and amplification all in one package. So you could make this a all active three-way pair, and the end user can get a 1 or 2 rack RU high package, and it can do everything. Now, in terms of one of them, linear research, I've actually seen what's unique about them is that the software interface that controls it is something anybody can use. So if you think that the end user would benefit from having, let's say, a 4-pole crossover and being able to EQ it at their option both before and after the crossover, that solution is readily available.
Well, so, anybody can build these any way they want, and use any crossover they want because this is DIY after all.
Mhm.
But I don't like steep crossovers. I avoid using them wherever possible. Um, and
Being a 4-pole,
well, 4-pole is 24 dB per octave.
yes. So
So,
does that classify as steep,
yes.
even if it's linear phase?
Well, are you achieving linear phase with FIR?
They are. Well, I know at least one is the linear phase,
Well,
linear research.
that's I mean that's fine. Um, and to each his own. But what I was very careful in this design, so that the acoustic slopes effectively on all the drivers are about 12 dB per octave. And so that curve that I showed you earlier, that's an acoustic slope of 12 dB per octave. And that what that means is that if the mid-range and tweeter are wired out of phase, then each of them has an identical phase curve, and they are perfectly in phase. And if you flip that, you get almost a complete null at the crossover frequency, which is what you want. And so I'm getting an effective 12 dB per octave acoustic slope. And then I'm using a very tiny amount of FIR DSP to straighten it out and return the system to complete linear phase. Now, if a person says, I've got a linear phase 24 dB per octave electronic crossover, it's only the electronic part that's linear phase. After you add the drivers and their slopes, it's not linear phase anymore. And it's not compensating for those issues. And so what I'm achieving is a system that's completely linear phase when it's all done acoustically, which is extremely rare. And so that's why I wouldn't mess with the design. If I were another user, I wouldn't mess with the design unless I really, really knew what I was doing. Um, it kind of reminds me of on DIY audio, somebody was they were converting a pair of Duntech Sovereigns from the 1990s to active. And the guy was all braggadocious about his 24 dB per octave crossovers, but he was completely missing the point of John Dunleavy's original design in the first place, which was to define a linear phase speaker, which is almost unheard of. And one of the priorities that I have in this design is to actually achieve linear phase, which is almost never done in speakers. I'd say one speaker in 200 is actually a linear phase speaker. And so, you know, people can argue about whether you can hear that and stuff, but I think you can, and you can definitely measure it.
No, I actually know you can, and I
Mm,
know you can measure it. In the pro world, when it's done properly, which, as you said, is almost never, what they do is they apply pre-EQ such that if they cross over, let's say, electrode is 24, it's after the system has already been compensated. And so that's very complicated. But I mentioned linear research because they have control software, for example, that makes it such that non-geeks can use it.
mm, yeah.
Um, and also, sorry for interjecting, but one of your end users said, "Oh, well, I didn't do the, if I got it right, I didn't do the bitches brew because I wanted it two-way because I wanted one cable." Pro World, you can get a Nutric 8-pole cable very easily. And so they could make a three-way system with a single cable.
Yeah. Cool.
Very good. The other, Justice, unless you had some comment, I had another question. Justice? No question. So I looked at the pictures. I noted that quite a number of your end users had the dipole very close to the rear wall. As a long-term user of dipoles, I would suggest that they step that out to at least 5, maybe 7 feet. And that makes an enormous difference in not only the imaging at the sweet spot, but off the sweet spot. You just get a little bit of extra space so that the rear wave doesn't come back in at least 15 milliseconds or so.
Okay.
The other comment was that you had noted that it was, if I got it right, that it was easier to EQ a dipole in a non-optimum room than a monopole. I actually would emphasize that. You can actually model at least a rectangular room, and you find that a dipole does indeed make it easier to, it smooths out the in-room response relative to a monopole. This is actually quite predictable. So you had pointed out the sidewall, easier to mitigate sidewall reflections. That actually can be modeled. It shows up very well in many situations. Alvin and Justice, you had anything you'd like to add or question?
I'm sorry, I have to have my my lunch. I'm sorry, not the most elegant show, but Perry, thank you for your time. I really appreciate that.
Oh,
I think my question really goes back to the first point that was made, like, you know, what is really, to what extent can it play 20 to 20 kilohertz at live levels? Can it play an organ at live levels without noticeable distortion? And I think you mentioned something about, well, we can shift the high pass up to 30 hertz or something if you want to go low. But I'm curious to see what the distortion measures are, what compression you get. And I'm sure for B and C, or I think I looked it up, I couldn't find any real high power distortion curves for it. but that would make it more interesting to actually measure it. Thermal compression, all kinds of intermodulation, or what can it do? And dipoles, of course, notoriously are limited in their low frequency. And yours is a 15-inch or is it 18?
The bitches brews have two 15s on each side. And a fairly deep cabinet. And the cabinet's what, 26 inches deep. So
Yeah.
the wings push the cutoff down pretty low. So I don't have a bunch of extensive measurements. What I can tell you is, I've sat in my room and fed sine waves into them and played loud music, and they're they're very clean down to about 30, and then if you're pushing them really hard, when you get down into the 20s, you can hear some distortion, but they'll play pretty loud. I mean, you
Yeah.
got two 15s on each side,
Yeah.
and the cabinet configuration, you're probably only losing 6 or 8 decibels at 20 hertz from the baffle loss. So, um, I've said in some of my articles, extreme bass heads, who play really loud EDM music and like to have their pant legs flat, that type of person may not be fully satisfied with the bitches brew of playing, 18 hertz.
Yeah. Supplement with a subwoofer.
But
Easy.
but 98% of listeners are not
Yeah.
like that, and they would be perfectly happy with them.
Yeah.
Now, in my room over here, I actually do have 12-inch sealed subs in the corner, and I have a setting on my crossover where I can turn on the subs, and the subs kick in at 27 hertz and they go down to 10.
Yeah.
And on about 5% of the music that I could play, you could actually tell whether the subs are on or off.
Right. Right.
95% of music doesn't even have anything down there at all. And so yeah, the bitches brews, I mean, they don't absolutely do everything that anybody could ever want them to do, but they're in the realm of the 98 or 99% of audiophiles would be more than happy and would never push them to their limits under any normal circumstance. And let's also keep in mind, you do have a DSP EQ, and you can EQ it to your heart's content. If you want to put 25 or 30 decibels of boost at 18 hertz, you can. I don't do that because I think, well, I don't really think it's necessary, but that's why I have my extra 10 hertz subwoofer, in case of emergency.
Yeah. Well, just to set the stage, I mean, I don't know where Alvin and Leslie are at, but so I have two sealed cabinets, each with four 15-inch woofers. And even those, even in that situation with acoustical music of variety of kinds, you can reach it, you can bottom it out, you can get compression. That is only going to be worse with a dipole.
Right.
So have you considered going to an 18-inch or a 21-inch, or, I mean, why stop at 15?
Oh, well, sure. Like, just buy bigger woofers.
Yeah.
I think one of the things that I value in a design is elegance. I felt like having three 15s, all the same size, all in
Yeah.
a line, was
Yeah.
it's visually pleasing. Women like them. The cabinets are beautiful. There's nothing to keep you from using 18-inch
Right.
woofers or 21-inch woofers, or having a giant subwoofer in the corner, or whatever.
Right. Yeah, no, for sure. And they do look stellar, especially the wood that you picked up at where was it? Like a wood shop in the middle of nowhere?
In Palmyra, Nebraska, there's a huge wood shop called Big Red sawmill, and it's a great place to visit. And then some of my other wood, I got it from here in Chicago, in Harvey, Illinois, in the south suburbs. There's another place, and considering that an open baffle cabinet is pretty simple, and you can afford to spend a little extra money on a
Yeah,
nice piece of wood,
absolutely.
and it's not particle board either. It's wood has so much personality.
Yeah, yeah. Well, the web factor being that high for something that big that can play so well, that is very impressive all by itself.
Now, you referred to another conversation where I talked about the smaller ones, the live edge dipoles, and they have the single 18. And I have two EQ settings on those.
Oh, very good.
One pushes them down to about 20 or 25 hertz, and the other one rolls off sharply below 30. And it it actually makes quite a difference if you just limit the bass to above 30. These things will play very loud, and most people will never notice that they're missing that bottom half of an octave.
Yeah.
And so the trade-off in a normal box, whether it's a horn, well, that I shouldn't say that. Well, I have to qualify this. In any normal box, the further you tune the box lower, every octave costs you 12 decibels in dynamic range.
At
So
base.
so if my system will do 110 at 60 hertz, it'll only do 98 at 30 hertz. And that would be the case with ported and sealed designs. But with dipoles, if you go down an octave, you lose 18 dB, not 12, because you're having the woofer limitation combined with the dipole cancellation.
Yeah.
And so that means every third octave costs you 6 decibels, which you can flip it around and say, well, if I give up a third octave of bass, I get 6 more decibels of dynamic range. So you just have to pick where how far you're going to try to go, and then not try to go any further than that and just roll it off,
Right.
which is what I do with the
Yeah.
DSP.
Yep. Yeah. Yep. That makes
Uh,
perfect sense. Have you done any sort of formal kind of evaluation with people? It's like, okay, well, here's a, yeah, I think there's AES has several formalized uh, here, auditory evaluation methods. I'd be curious to see what people think are the strengths and the weaknesses, if there are. I mean, everything is a compromise, right? Be interesting to
Um,
know about that. 'Cause you're saying like 98% won't miss it. Maybe that's true. I don't know. I mean, there's a difference between low frequency extension and high dynamic range capability and just, having a poor EQ. Poor in some person's perspective, I guess.
well, I haven't done any formal kinds of stuff. I like the Chicago Audio Society came over a couple years ago, and I had 30 or 40 people in the house, and and everybody listened to music for a few hours, and some of the comments ended up on the DIY audio forum, and you probably saw them. And um, I had a few people say they were the best speakers they've ever heard. Um, I didn't have everybody say that, but if you get a few people in an audio club saying that, you've hit
Yeah.
some kind of a mark.
Yeah. Well, it's just it's totally coherent with the constant activity. It makes perfect sense. But I think there's some. So, to what extent do you acoustically treat your? So I think you mentioned. No, I'm not sure what you said. To what extent do you treat your room?
So my room, I got I've got a library with the bitches brews, and then this room right in here has the live edge dipoles, and the two rooms adjoin. The library is just the library, and it's got books all over the place, so it's kind of well damped, and it's got a rug. And I don't have any other particular acoustic treatment in the room. I use EQ to solve. There's two room there's a room mode at 40, and there's another one at 75, and I just put notch filters in the DSP, and those seem to take care of it pretty well.
Yeah.
This
Yeah.
room has windows on three sides. It's a much more live room, and it definitely sounds different. And I don't have any special treatments in here either. And I have some EQ notches at the frequencies that this room resonates at, and that seems to work
Yeah.
fine.
Yeah. 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 Yeah.
And I'll be the first to admit that you can be as sophisticated as you want to go with room treatments, and that's like just a whole
Yes.
deep rabbit hole that some people choose
Yes.
to go down.
Yes. Well, like you said, to each their own. It's you can do it if you want to spend a lot of money on it. I had a completely unrelated question. If we can segue away from audio for a second, Alvin, is that where do you have any more?
No, go ahead.
Yes, yeah. There is a mention of the origin of the genetic code.
Yeah.
I'm a biologist and
Yeah.
neuroscientist, and I'm not sure what you mean by that.
Well, so I wrote a book called Evolution 2.0, Breaking the Deadlock Between Darwin and Design. It came out 10 years ago. It's endorsed by people from Harvard, Oxford, UCLA. And I organized a $10 million prize for the origin of the genetic code. And the genetic, so DNA transcription and translation are functionally identical to encoding and decoding in an electrical engineering context. You have a source code. It gets translated. So it's DNA gets translated into messenger RNA, which gets translated into amino acids, and that is functionally identical to I send you a text message, it gets converted to ones and zeros, it goes through the air, and it shows up in your phone as a text message.
Mhm.
And so the fundamental question in genetics is it's not how do you get a DNA strand, it's how do you get a DNA strand to carry a code that follows a specific convention, like you see in the genetic coding table in any biology book, where GGG equals glycine and AAA equals lysine, and so forth. And you have the 64 mappings of the genetic code. And so there's a very fundamental question in the origin of life on Earth, which is how did you get a code without starting with a code? And I quickly found out that nobody has any idea where the genetic code came from. There are all kinds of hand waving explanations about, well, there was a lucky RNA strand and it started mutating and it became a self replicator. And all of these explanations are extremely patchy. I mean,
Yeah.
most of it is hand waving.
Mhm.
And I said, well, I think this is the most fundamental question in science that can be precisely defined. It's a huge question about the origin of life. So I went out and raised money from a group of private equity investors, and I put together a $10 million prize. And we announced it at the Royal Society with Oxford professor Dennis Noble in 2019. And it was written up in the Financial Times a couple days later, and you can go look it up. And we have a website where we wrote a specification. We said, basically, if you can pour chemicals in your bathtub and you can get the chemicals to self-organize into an encoder on one end and a decoder on the other end, where a message is being sent from A to B, and translated as such, then if you submit that to us and it's patentable, we'll patent it, we'll pay for the patent, we'll pay you $10 million, and we'll partner you into the company that we form around that technology. Because I think when you have a question that's that deep, it's not just a philosophical question, it's also an engineering question, it's a business question, it's a science question. And I think billion-dollar questions deserve better than 25-cent answers. And I know an awful lot of people in the origin of life field. And if you look around, I've got interviews with Lee Cronin at the University of Glasgow. I've got all kinds of people that are in that field. And so I think if somebody figures this out, it's bigger than Google, it's bigger than ChatGPT, it's bigger than the discovery of the genetic code. It's like one of the all-time greatest mysteries of science. And so I spend about a third to a half of my professional life in science, working on questions like that, in addition to the consulting and business strategy business that is my main bread and butter.
So were you in genetics before then, or
No,
you still are?
no. I am an electrical engineer by education, and in 2002, I wrote an Ethernet book, and it's called Industrial Ethernet. And at the time, factories were starting to use Ethernet as a low-level industrial network, which is really a very different kind of application than typical routers and things that you see in your house and business.
Mm-hmm.
So I wrote that book. I was in the networking field for probably 6 years, mostly industrial automation. And so I had written that book. In 2004, I went to China to visit my brother. My brother was a missionary who was teaching English, and he had gotten a seminary degree. And he was working at a hotel, and he had a job teaching English, and then he was doing missionary work on the side. And we're both pastors' kids, and we were both raised in a religious family. And he said to me, Perry, I don't believe any of this Christianity stuff anymore, and I'm quitting my job and going home, and I'm not a Christian, I'm an agnostic now. And I was like, what? And we got into an argument, and I said, Brian, look at the hand at the end of your arm. This is a nice piece of engineering, and I'm an engineer. I should know. I said, you don't think this is an accumulation of random accidents, do you? And he goes, hold on. And everybody's heard this argument before. You don't need any designer and you don't need anything like that. You just need random mutation and natural selection. And if I have a billion falcons flying around, there's going to be genetic mutations, and one of them is going to make them see better. And then they'll out hunt the other falcons, and there's this ratchet, and it just gets better and better. And now at the time, I had never really studied evolution. I didn't have a strong opinion about it. I had a intuitive engineer sense that this does not look like an accident. And I thought to myself, I had two thoughts. The first thought was, in all my years of engineering and all my engineering school, in everything I've ever done in my career, I've never seen what he just described to me actually work. I've never seen anything just accidentally replicate and get better and better and better. I've never seen it. This doesn't make any sense. But at the same time, I had this other thought. And the other thought was, I bet there's a whole bunch of biologists that would agree with him and they would not agree with me, and they can't all be stupid. And to be honest, I don't think I know. And we're making ourselves miserable having this argument. I'm just going to stop right now. I'm going to stop arguing with Brian. He is really pushing my buttons, and he's provoking a lot of huge questions that I think are valuable questions.
Yeah.
I am going to go home and I'm going to figure this out. So I went home and I started buying books. And I'm like, so what is the deal with all this? Now, again, I didn't really have anything against evolution, or I wasn't like such a conservative that I would be anti, I wasn't that flavor of person. But
Yeah.
I, I was I was not buying the assertion that billiard balls just banging around in the universe will eventually produce falcons. Because as an engineer, like I've never seen that happen. So I go down the rabbit hole, and I found it to be extraordinarily challenging and difficult. I think biology is about 100,000 times more complicated than electrical engineering. I think, whatever makes a cell work or whatever makes a blade of grass is light years more sophisticated than any of the stuff we argue about in our audio circles, or even Google or anything.
You never get bored in biology, that's for
And
sure.
and and there was a point, I was several weeks into this, and I had this epiphany. I was trying to understand the genetic code and mutations and replication and how DNA replicates. And all of a sudden, it just hit me like a ton of bricks. Wait a minute, I've seen this before. This is the exact same stuff
Yeah.
that's in my Ethernet book.
Interesting.
It,
Yeah.
it like it and it
Yeah.
really is. And then
Yeah.
I went into the literature. There's an entire field of biology called information theory, where they've applied Claude Shannon's Bell Labs work to genetics and all the rest of it. It's a very well developed field. And I realized evolution is a software engineering problem.
Yeah. Yeah.
And what I discovered was that in the mainstream media, in evolution, and it was true 20 years ago, it's still true now, that the entire field had been crippled by a polarization. You know, the word polarization that we now use in modern politics that everybody is so irritated about? That exact thing had already happened. Basically, the creationists and the atheists had collectively butchered the entire conversation, and they were not neither of those sides was telling you anything that was really actually important about evolution. They were just arguing these surface level talking points. And what I discovered as I went deep into the literature was that there were people like Barbara McClintock and Lynn Margulis and James Shapiro and a whole bunch of other people who had very meticulously figured out that evolutionary events are highly engineered restructurings of the genome and of the organism, that they're highly calculated, and that every organism down to the cellular level is extraordinarily intelligent. And the first of this that I really started to understand was Barbara McClintock's corn plants, because what she did, this is in the 1940s,
Hmm.
she would use radiation to damage the chromosomes of corn plants. And she was just being like a hacker. She would try stuff, and she would damage chromosome with some radiation, take the radiation away. She would study the chromosomes under her microscope, and she would figure out how the chromosomes were being rearranged. And what she figured out was, so here's like a computer program analogy. You could think of the corn plant's genome as a computer program where the radiation knocked out some of the lines of code. And we all know what would happen to any computer program if you just randomly knocked out some lines of code. It would generally completely destroy it, and it wouldn't work, and it would crash. What the plant did was, the plant was trying to reproduce. It could not reproduce because of the missing code. And it went to another part of the program and it copy pasted code into the missing stuff. And it was not the same stuff, but it was good enough, and
Yeah.
it produced an innovation that caused the plant to evolve, and it went on to reproduce. But it actually it improvised in real time to deal with the missing information. And basically, this is how evolution actually works, is it's not a result of random copying errors simply filtered by natural selection. That would pretty much never work. What it's actually doing is the organism is aware of its own genetics. It's aware of all the different parts. And when it's confronted by a
Hmm.
threat,
Hmm.
it will generate an innovation. And nobody really knows how it does this.
Hmm.
Um, a, a, a word that has come into strong usage in the last 10 years in biology, in evolutionary biology, is cognition. And cognition is like a more conservative substitute for the word consciousness, is is that the organism has some level of self-awareness. And so I've been down this rabbit hole now for more than 20 years. I'm part of a cancer early detection company that's using these models to pick up
Oh, yeah.
cancer.
Oh,
Or,
yeah.
and if you go look on my YouTube channel, and I have a podcast called Evolution 2.0, you'll find all kinds of interviews and conversations about this view of evolution as applied to philosophy, religion, medicine, bioengineering, all of these things. And so what started out as a religious argument between me and my brother turned into this whole technological journey.
Yeah.
It
Yeah.
just keeps
Yeah.
getting more and more interesting.
Yeah. 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 Well, you obviously have a very open mind, and you're curious, and that leads to some really interesting and clearly also very good sounding loudspeakers.
Yeah, well, you know what? A lot of, I have to say that my speaker design experience gave me a lot of instincts when I went into biology. So
Yeah.
so let me try to like make all this come full circle. When I was a junior in college, um, so this was 1990, there had been some literature on transmission lines that speaker aficionados are probably heard about. People like Bailey, writing these papers. And at the time, um, designing a transmission line speaker was this extremely like sling mud against the wall sort of affair with these little rules of thumb, and it was hardly, you could hardly consider it a like a real actual model.
Yeah.
It was just a mess.
Yeah.
I took an acoustics class in electrical engineering school, and I decided to write a term paper on transmission lines and develop a model of transmission lines. And if you go search on my websites, you will find this because I published that paper, and it's on my website. So I wrote this paper in 1990, and I discovered that I had to literally start with the laws of physics. Force equals mass times acceleration. I have a speaker cone. It has so much current. It has a BL. It has resistance. It has compliance. It has surface area. I'm going to put a speaker in a tube. The tube is this long. I'm going to work out the wave equations. And I worked out all of this stuff. And it took me several months. I found out that there were mistakes in the AES paper. There was a sign error in one of the equations, and it took about 3 weeks for me to figure out that the equation was wrong. I
Whose
was
paper was that? Well, maybe
I
we should
was
not mention names.
I was running simulations on my Hewlett Packard 28S calculator that I bought for $200, and it's making like one little dot every 2 seconds and making so, so like I did all this, and when I got done writing that paper, I did figure it out. I derived the math of a transmission line speaker enclosure I could load the equations into my calculator. I could put the Q and all that stuff in. I could figure out what the response was going to be. And I had the satisfaction and the embodied experience of getting to the bottom of the swamp of how
Yeah.
a device works.
Yes. Yeah. Yeah. Yeah.
And engineers who've done this sort of thing know that there's this confidence and the satisfaction. I
Yeah.
figured it out.
Yes.
I started with Newton's law, and I got in. And by the way, I was going to the library and getting acoustics books. I was looking at my electromagnetic fields and waves book, and I was comparing the acoustical models to the electrical models and all of that, and seeing how the analogies flow. So I published, I wrote the paper, I turned it in, I got an A. I had the experience when so fast forward, I guess it's 14 years later, and I'm having this argument about evolution. And I'm listening to all these people argue about stuff.
Yeah.
And I thought, I am looking for that sensation that I had when I wrote that paper where I know how this thing works.
Yeah.
And and my first sense of having that sensation was when I connected the dots between Ethernet and information theory and genetics. I'm like, well, an electrical engineer can understand genetics because it's all basically ones and zeros. It's just a quaternary code instead of a binary code. Well, so then you find, well, that takes you so far, but it doesn't take you as far as you think it does, because genetics does not do what the popular media and the textbooks tell you it does. So, for example, the Human Genome Project, the human genome was sequenced in what, 2001, I think? And they're like, da da da. And they said for the 10 years that they were doing that, when we crack the human genetic code, we are going to solve so many diseases, and we're going to be a new era of medical history. Well, it was only about half true.
Yeah.
It turns out, so my good friend Dennis Noble at Oxford, he's 89 years old. He's a titan in physiology. You can go look him up. He's a physiologist, and he says, I can learn more about a person's health taking their height, weight, girth, and heartbeat, and pulse, and blood pressure.
Yeah.
I can predict your health better from those 4 or 5 things
Right.
than I can from sequencing your entire genome.
Yeah.
And there are only a few diseases where you can solve the disease by fixing a genetic mutation.
Yeah. They're quite specific.
Most of them you can't.
Yeah.
And the genome does not do as much as people think it does. So, for example, body plans are not encoded in the genome. The fact that you have 2 arms and 2 legs and a head and a torso is actually not in the genome. It's encoded in other things.
Epigenetics, of course.
There's epigenetics. There's also bioelectric fields.
Yeah.
I've got a friend named Michael Levin at Tufts University. Boy, if you want to go down a rabbit hole, just go on Michael Levin's YouTube channel and start watching stuff. It will blow your mind. He is an expert on bioelectric fields, and one of his areas of specialty is amphibians. And he studies, why is it that like salamanders are able to regenerate amputated limbs and most mammals cannot. Now, if you study salamanders regenerating their limbs, you will be astounded, because it doesn't matter where you cut the arm off. Wherever you cut it off, it will start growing.
Yeah.
And it will grow a new arm and a new limb, and it will stop when it's supposed to stop, and it will still be symmetrical on the right side as to what it is on the left. And it knows how to do all that stuff, and none of it is encoded in genetics.
Huh.
It's actually encoded in bioelectric fields. And The cells, they use ion channels and gap junctions to generate an electric field that goes where the arm is supposed to go, and then the tissues grow into that electric field and they follow it, and then the cells multiply. They So the bone tissue will multiply, and the muscle tissue will multiply, and the skin tissue will multiply, and they'll continue to multiply until there's a certain amount of pressure against every cell from its neighbors, and then it will get a signal to stop.
Is he arguing that chemical gradients don't play a role? Because that's quite more
Well,
typical in mammalians. Or
that's part of it too, and I'm not a chemist, and I would probably just embarrass myself if I
well,
tried.
it's not my region of interest or my expertise at all. I mean, biology is so vast.
And so I was starting to say how audio my audio sensibilities were extremely helpful. There was the transmission line story, but
Did
then
you
there
get
was,
into Audio Express or Speaker Builder? Because there was a whole big series on, like, was it quarter pi or something, whatever it was.
well, I never went on and published that stuff in Audio Express.
Okay.
Now, here's what did happen. There were some other people, like there's a guy named Martin King, who is well known in the DIY audio community, and he
Yeah.
built models on MATLAB where
Yeah.
you could simulate transmission lines. And then more recently, there have been some other programs like HornResp, and where you can enter your drivers, you can design your box, and you can say what are the dimensions of the tube, and what's the taper ratio, and where is the driver positioned relative to the end, like within the line.
Yeah.
And you can play with all of that and generate very nice simulations. And so these are, like, it's one thing for me to write a paper that has the equations and to know that the equations work. It's another thing for somebody to build a computer program
Yeah. Totally.
where a person can
Yeah.
reasonably,
Yeah.
figure it out and put it all in there. And so I've used those programs to model, and I've built transmission lines and horns and all of that stuff.
And
And
it doesn't mean that you understand it, but at least you can predict it, which is not the same thing.
yeah, and another thing, okay, so audio people, they have much more appreciation than most for the notion of an original pure signal. It's almost a religious concept in the audio world that you have this recording of Miles Davis, and it was recorded in 1959, and it's the best we've got, and all we can do is preserve it, and we shouldn't be messing around with it. We just and we're going to play it as cleanly as we can. We have this concept of preserving a signal. Now, biologists don't really have that in their DNA. They take a lot of it for granted. They're like, well, I got a dandelion or I got a frog, and it seems to work. And they think that their theory of how it works is how it works. No, that's your theory of how it works. How it actually works may be completely different than that. And what I understood was this notion that we're just going to introduce some random genetic mutations, and then natural selection is going to clean it all up. Any audiophile knows better than to believe that. That would never work on a U2 CD, and it would never work on Miles Davis, and it doesn't work on DNA either. And so that's how I came to discover, oh, well, there's this whole other body of literature about how bacteria or protists or corn plants or frogs actually modify their DNA. There are so many things going on. It is absolutely crazy. So, for example, there are these things called exosomes, which it turns out, when you are living in an environment that has certain hostilities and challenges, exosomes from your body will travel to your reproductive organisms. And an exosome it's like a smaller than a cell. It's basically a signaling virus. that the body produces and to send from point A to point B. And so it packages these little RNA messages in a protein packet, and it sends them elsewhere in the body, and they will actually go to your sperm and egg cells, and they will reprogram the sperm and egg cells so that your progeny is adapted to this particular environment.
Didn't know about that. Okay, that's interesting.
And so that means that evolutionary changes are directly heritable. Well, that was considered apostasy 20 or 30 years ago. It was considered utterly absurd and ridiculous that
Yeah.
that you could have a physical experience of living somewhere, and that physical experience would directly affect your offspring immediately when you go have sex and have a baby. But it turns out to be true. And what's funny historically is that Darwin believed this. Now, you have to remember how little Darwin would have ever understood about genetics or anything in 1859. And Lamarck, who came before him, was a very strong champion of this theory. I was giving a presentation on this one time, and this guy goes, "Well, I'm a farmer. I know this. How come the biologists don't?"
Yeah,
Like
yeah.
the farmer knows it experientially. And so I discovered that there's all kinds of dogmas and shibboleths and sacred cows in biology that many times
Yeah.
have nothing to do. Well, it's just like the audio business. We know how many dogmas and
Yes.
weird ideas there are. And I feel like my journey through audio was a really good preparation. And well, guess what? There's more religious arguments in the world than you think there are.
It's true. Yes.
So that's
Certainly
a long
also in
answer to
neuroscience.
that's a long answer to a short question.
No,
That's
that
fascinating.
was good because we all had that same question about the $10 million prize. So one last question. It has been an hour. Dipoles, not dipoles, but coax speakers
Yeah.
are not known for creating a good waterfall plot. Have you looked at?
Oh, okay. So let me make a huge distinction here. So now I worked at Jensen in the 1990s, and of course Jensen was famous for its coax and triax speakers, and so a Jensen coax looks like this. You've got a cone, and a driver like this, and then it's got a bridge across the middle, and then it's got a little tweeter here. This is terrible. It is absolutely terrible. There is no way to make this work well. And here's why. It's because let's say we're talking 3,000 or 4,000 hertz, where you're typically crossing over from a woofer to a tweeter. Let me use a green marker. The waves from the tweeter are bouncing off the woofer cone and reflecting back. And you get this horrible comb filtering that you cannot get rid of. It's terrible. Okay, now let's talk about the kind of coax that I use in the Bitches Brews and live edge dipoles. That coax, here, let me use. So I have a woofer cone, and then there is a right inside the woofer's voice coil is a metal fixture that serves as a horn. So the woofer cone is is merely an extension of a horn. And there's a throat, and this is a compression driver firing into the back of the woofer magnet. And so in my designs, this cone is always a mid-range, not a woofer, so that it doesn't have a lot of excursion. In none of my designs, if you're playing at any sane volume level, you can't even see the cone move. And so the cone is a horn for the compression driver. And it means that, so in the bitches brew, you've got about it's a 15-inch woofer, so it means the cone's about 12 inches in diameter. So the woofer acts like a 12-inch woofer, and it has the directivity characteristics of a 12-inch woofer. Well, then when the compression driver kicks in, it has the characteristics of a 12-inch wide horn. Now, if you look at a lot of like if you just go to a club or a bar down the street, you will it's almost ubiquitous. You will see like a two-way with a 15-inch woofer and a 15-inch horn like this.
Okay.
And the horn is the same diameter as the woofer. And that's very deliberate. It's because it will then give it the same radiation pattern as the woofer. And in a 15-inch, usually the crossover is about 1,000 hertz. And this design will give you, so at low frequencies, it's omnidirectional, and you get up to 300 or 400 hertz, and the 15-inch woofer has a narrower radiation pattern. And then when you get up to 1K and you cross over to the horn will have the same radiation pattern. And then if the horn is constant directivity, it will maintain that radiation pattern all the way to 10 or 20K. And so this basic design of PA speakers is actually quite good. The basic idea is pretty sound. What this is doing is it's collapsing the constant directivity horn into the woofer so that the woofer is the horn. And this was Tannoy's brilliant idea 50 years ago. Okay, so what are the problems that you have? It's not perfect. So what are the problems? Well, the problems are you're prone to have some problems in this transition at the cone neck. And most compression coax drivers will have some squiggles in the frequency response where the horn is not perfectly flat response. And some designs do it very well and some don't. And you can go look at all the different, there's dozens of these different drivers on the market, and you can go look at them, and some of them do a better job than others. I think B&C does a really nice job. I think Radian does a really nice job. And so I am able to fix the few problems that remain with DSP, and I get a completely coherent driver where once I've got my crossover designed and I showed you those curves, I submit to you this is as seamless a crossover as you have ever heard in your life. The radiation pattern is exactly consistent. In fact, let me show you, because I think this is important. All right. So this right here, let me zoom a little bit. So this is the Bitches Brew on axis, 15 degrees, 30 degrees, 45, 60, 75 degrees. Now, it's kind of messy here around 100 hertz, and that's because I'm measuring this in a room, and I just don't, I don't consider the stuff below 200 hertz to be particularly accurate. But that's not the point anyway, because we're talking about a 2 or 3 kilohertz crossover. Do you see how evenly constant directivity this is from on axis all the way to 75? You go 75 degrees off axis and you've lost about 10 decibels. And then here's another representation of the same data. This is absolutely beautiful. You almost never find a speaker with a radiation pattern this consistent and this close to actual constant directivity. And in the graphs, I don't know, is this little squiggle here where the crossover is? Maybe. You really can't even tell where the crossover is. And then if I look at, let me show you the, oops, that wasn't the one I wanted. Here we go. So here's where I think the proof is in the pudding. This is the step response. It's almost perfect. And so all of the timing issues between the mid-range and tweeter have been resolved. And this is the impulse response. Most speaker manufacturers would never even show it to you because it's just a bunch of squiggles. But this gives you this very short, clean impulse, and then it dies off pretty fast. Well, the audible result of this is that the resolution is just incredible. And, little percussion instruments, or like if somebody's playing ghost notes on a snare drum or wire brushes, like really delicate sounds like that are actually quite hard to pull off convincingly. They sound really good. And so I really like what you get from a compression horn professional coax, which is a completely different animal than this. Yes, Leslie.
Given what you've said, I actually think there is an explanation for the extra perceived headroom of your design in the base. So I used to be a physicist, and around the 90s, I made a transmission line dipole for, of all people, Alvin Foster.
Okay. Yeah.
And I had worked out, like you did, the math, and what I figured out was it should be able to play a lot louder. So I've done many dipoles since, and what happens at the bottom end of a bass dipole speaker is the headroom actually drops off even faster, another 6 dB faster, when you include nonlinear distortion. However, above that, the bottom of that bandpass, for 2 octaves above that, you actually have more headroom relative to a monopole. And when you do an integration playing a music waveform, or maybe the M noise, and you average it out, The dipole actually has considerably more total headroom playing music than a
Mm,
monopole. So I've
mm.
actually went through exercises. I built actually I didn't, it was Stanley Marcus made a uh, dipole which went down to 16 hertz. And it was big as two refrigerators, etc. And I had another BAS member, um, DB Labs, he's an electrical engineer. He made a 30 dB EQ and it worked. But the wife approval factor was you're divorced.
Yeah, yeah.
But playing down to 30 hertz, 30 up through, let's say, 100, and since most bass music with most music might center around 50, you actually have much more effective headroom with the dipole than a monopole with exactly the same driver.
Yeah, so can I repeat back to you what you told me in a different using
Yeah.
in a different frame? So let's say I have a bass reflex speaker. And this is my port, and this is my woofer, okay? Well, the bass reflex is going to have a tuning frequency. And so let's say it's tuned at 30 hertz. So that's going to give me, I'm going to get a frequency response that looks like this. And this is the part nobody pays attention to is if I graph the excursion of the woofer, here, it looks like that.
Mhm.
So,
Mhm.
so if I put a sine wave in at 200 hertz, I'm not going to see the cone move very much. And then I sweep it downwards and I'm going to see the woofer it's going to start flapping really hard and it's going to max out at probably about 45 hertz. The woofer cone is going to be flapping hard. Then when I get close to the tuning frequency, the woofer the woofer excursion narrows a lot because the port is doing all the work. And the Helmholtz resonator is pulling against the woofer. So like when the woofer is trying to move forward, the box is pulling it back and then the sound is coming out of the port instead of the woofer. And so at 30, I have a huge amount of leverage and this reflex speaker will play quite loud at 30 with not much woofer excursion. Then as soon as I go below that tuning frequency, the woofer just goes crazy. And what most people don't realize is that if you do not roll off the woofer below the tuning frequency, you get a whole bunch of wasted motion that doesn't do you any good.
Mhm.
Now, if you have a small reflex speaker like a 6.5 inch two-way and it's tuned to 50 or 60, there's a whole bunch of music down at 30 or 40 that's stressing out that woofer, and it's a major problem. If you have a big pair of speakers and they're tuned at 30, there isn't typically a lot of music down at 20 and 15, and so you tend to get away with it. Now,
Mhm.
what I just heard you say was um, that when you compared the actual measurements in real music situations of a speaker with this kind of behavior versus a dipole that has a very different response, in aggregate, you actually got better response from the dipole.
Yeah,
And
and
there's
was
there's
predictably
another,
so.
sorry,
And predictably so.
and there's another reason that we haven't even discussed, which is the compression of air inside a speaker box is nonlinear because it's a very confined space. And it's possible for the dipole woofer to have a more linear suspension than the air spring in a box.
Yes.
And hardly anybody talks about that.
Even though it's quite predictable.
Yeah. But well, you have to know a few things about acoustics to know that that is true.
This is true.
This is not typical stereophile conversation that we're having here. You said you're a physicist, right?
I used to be, yes.
Well, once a physicist, always a physicist, in my opinion. So like, if somebody says the non-linearity of air compression, you know what they're talking about.
I have to quantify it, in fact.
Yeah.
Yes.
So that's another reason why dipoles can really what you do with a dipole is you make up for that cancellation loss by having more cone surface area. You just use a larger woofer. And a larger woofer can frankly atone for a multitude of sins.
I would also add that above the bottom of the bandpass, the dipole reinforcement with a music signal reduces the amount of nonlinear, that is intermodulation distortion, relative to a monopole. So like you have that vertical line there at 30 hertz. So let's say you went from another octave and a half above, maybe 30 to 80 or so.
In here?
Yeah, so 30 to 80. So the dipole would actually have less intermodulation, not talking about harmonic, but less intermodulation distortion than a monopole.
I think you might be suggesting that the dipole excursion looks maybe something like that.
Yes, it's because the rear wave, their frequency is above the bottom of the bandpass, where the rear wave reinforces the front. Therefore, there is, for a given sound pressure level, there is less excursion. Less excursion means less amplitude modulation.
Yes.
Not that frequency modulation that won't happen at this frequency. But the reason why in the beginning we asked if you use the M noise is because that was one of the first few standards we've seen where they actually say, yes, intermodulation distortion is important. And it shows up benefits like we just described more than your ordinary sine wave sweep. And so, so I'm positing, like when people say, oh, the bass sounds cleaner, it's because it is cleaner.
Yeah, I think you're right. I think you have to have a good woofer to begin with. Otherwise, you got a problem. But yes, if you have good drivers, there's a lot to commend it, and it's just one of those funny little things that most people, I don't know that most people have ever heard of dipole, other than a magnepan or an electrostatic, but that's a whole different.
Oh, yes.
Okay, well, how are you doing? It's almost 3:30. So we've kept all of you. So are you satisfied, Justice?
I think it's lovely. Yeah, it's been a great discussion, and I learned a few things. Certainly, also, but surprising enough.
So you're gonna claim the $10 million?
Well, what if I come up with a code that's not quaternary, but maybe biologically binary as well? Would that qualify?
Any actual code, if you go read the specification, and we also have a GPT. If you go look at the website, we have a GPT, and you go play with it.
Oh yeah.
Any like ternary, quaternary, binary, hexadecimal, like it just it has to be naturally occurring. And we get submissions all the time, and nobody's ever come close. I think it's a pretty difficult problem. And the speaker thing, I could take you guys down one other rabbit trail if you're interested.
Yes.
But I've never heard anybody talk
Always.
about.
Please.
Okay. I had a crazy idea a couple months ago, and I decided to do some experiments. And so you remember I said that I had these subwoofers in the corner
Yeah,
of the Bitches Brew room.
right.
So let me draw the room and tell you this little crazy theory I had. So here's my library, and here's my Bitches Brews. And here's me sitting there on my couch, right? And I've had these subwoofers in the corner for 20 years. And they don't get used very much. And one of the things that I noticed was getting a monopole subwoofer to blend with a dipole speaker is harder than it sounds.
Mm.
It's like you can hear the seam. Leslie seems to be nodding, like, yeah.
It's because that problem was identified and a solution which might not be wife acceptable by a BAS member. What, in the 80s? It's Sue, Alvin. You may have heard of Sue
Closer.
Research.
Sue Research.
Yeah,
Oh, HSU.
yeah.
Yeah.
And so I had for decades huge Sound Lab electrostats. And
Yeah.
I had the problem you just described.
Yeah.
And so Sue suggested, well, since you're not married, there's an obvious solution.
Hmm.
So you take those two subs and you put them a meter or less to the side of the listening position,
Like over here.
or even closer. Well,
Yeah.
whatever, a meter or less
Okay, like
of
there.
your listening position. Yes, on either side. And you
Yeah.
do that in stereo. And then what happens is, one, you need much less EQ for frequency response. You need much less level for the same amount of headroom, and the room is much less of a factor. So it's easier to get something which blends with the dipole. And
Okay.
this works.
Hmm.
Yeah.
Well, I think that's valid.
Yes.
So let me tell you about. I went on like a totally different rabbit trail with this, and I learned a few things that I never knew before. So I thought to myself, well, I got this subwoofer in the corner. What if I used the subwoofer to cancel the back wave of the dipole?
Whoa.
And then the front wave would go all the way down to, 15 or 20. And since I've got a digital signal processor and I can EQ this sub any way that I want, let's try it.
Whoa.
Well, it didn't work out the way I thought it would. So what I did was I put a microphone in the corner about a foot above the subwoofer. I had to think about this for a while, even to figure out, well, where do I put the microphone and where do at what point do I consider myself to have canceled it out? There's a lot of points after all.
Mm.
I finally decided, well, I think right in the corner, a foot above the subwoofer is a pretty good spot. And and then I meticulously tweaked the EQ of the sub so that it exactly matched the back wave that was firing into the corner.
Mm-hmm.
And I got the null.
Whoa.
And I had measurements. And so I go, okay, cool. I canceled it out. And then when I moved my microphone to the listener position, what I expected was going to happen was I should get more bass. Does that sound reasonable?
Mhm.
I got less.
Oh,
And it took me a few days to figure out why. Now,
Cancel much?
what do you guys think? What, you guys take a crack at why would I get less space in the listening position if, after all, I canceled out the back wave with the subwoofer, so
okay.
I should hear the front more.
Maybe you were canceling too much.
It gets, no, I see
Gain
it.
issue.
It's, I can't remember his name. He's a famous acoustician, but if you apply the method of images to your room,
Mm-hmm.
so you can actually model any rectangular room and replace all the walls with a set of 26 point sources. And then the room is equivalent to those 26 point sources plus their reflections back to some high order, maybe fifth order. And so
Okay.
what you've done is you've turned two sources and they're out of phase. And so at some frequency, low frequency, they're going to essentially be one source where you've now canceled out the bass from. So now you're replicating multiple sources where the amount of deep bass is reduced. Therefore, at the listening position, you will get less bass.
Well, what do you make of the fact that I did get that null in the corner?
But
It
you would
was about
expect that.
huh?
Yes, you would expect that. You're replicating a null now rather than a positive source.
Well, so I think I figured it out. And so I think you're basically right. And here's what I figured out. These walls reflect.
Yes.
And so if I want to think about reflections accurately, so imagine like this wall is a mirror and this wall is a mirror. And if I was looking in those mirrors, what would I see?
Exactly.
Well, a I would see a mirror image of subwoofer, subwoofer, subwoofer,
Yes.
subwoofer, subwoofer, subwoofer. And I would see a mirror image of speaker, speaker, speaker. And when I draw these speakers in, now I can imagine that I just took the walls away.
Exactly. That's the
And
method of images.
what I'm really listening to is three other images of speakers
Yes.
as I would hear them in my listening position. And what I realized was, wait a minute. I I hear, let's use different color. So if I put a plus on the front side of the speaker for the polarity of the wave and a minus on the back side of the speaker, at my listening position, this speaker's basically canceled out because I'm on the 90-degree edge. There's not really much wall reflection effectively, but I have, for every plus I have in the room, I have minuses in the mirror image.
Yes.
And I'm like, wait a minute. You know what that means? That means below about 100 hertz in an actual room, most of the sound of the dipole comes from the reflections from the back of it, not the front.
Mm-hmm.
And so that means if I null out the back wave, I get less bass at
Yeah,
the listener position, not more.
that's what that acoustician would say in his method of images. I'm blanking out on his name, but he wrote how to do this maybe 20 years ago or so.
Oh yeah, I wouldn't be surprised if somebody wrote about this 80 years ago. You know, it's pretty
Yeah,
basic, but but it it made me realize I've never heard any I've never heard anybody talk about the fact that most dipole bass that you hear in a real room comes from the back side of the dipole, not the front.
yes. Um, Dr. West of Sound Lab talked about that some, what, 40 something years ago or more.
Yep.
He was a physicist, and his was the first dipole I bought. And he did talk about this. And he actually originally had both dipole and monopole subs, and eventually went to monopole sub for this reason. Um, go ahead
Well,
with your audio.
so what I was like, well, that theory kind of fell flat on its face. And so then I decided, well, let's try a different approach with my subwoofer. So part of my strategy with the subwoofer was also to delay the subwoofer signal about 3 milliseconds so that it was canceling the wave just as it was coming in. So I did account for that too. What I realized was when you cross a subwoofer to a dipole, you want to cross it so that the subwoofer, let me draw a frequency response curve. So let's say that this is where my dipole is rolling off. I want my subwoofer to be timed to reinforce the back wave of the speaker below, in my case, 27 hertz.
Mhm.
And my tentative conclusion was that if I delay the subwoofer so that it's in perfect step with the back wave, rather than firing first and then reaching, uh, so that so let me explain. When I tried to do it a few years ago and I didn't feel like the result was that great, what I had done was I had the subwoofer fire first so that 4 milliseconds later, when the wave is passing the front side of the dipole, then the dipole fires. And that seems perfectly sensible. But what I realized I need to do was the dipole needs to fire, the back wave needs to go here, and then the subwoofer needs to fire when the back wave gets to the wall, and the subwoofer needs to reinforce the back wave at this frequency and below.
Okay.
And so this sub goes from 27 down to 10, and it blends really nicely.
So it works with a delay of what, 5 or 7 milliseconds?
More like 3 or 4 in my room. But you know, when you said you recommend 5 to 7 feet,
Yeah,
then you would put the delay at 5 to 7 feet.
gotcha,
Yeah.
gotcha. Okay, okay.
So you know, your mileage may vary, but That was a very interesting little discovery, and I just thought, well, how interesting that I've never read or heard anybody point out that most dipole base comes from the backside,
Yeah,
reflected from the room.
yes,
So, end of rabbit trail.
okay. If I might, back to your favorite topic of the design, I'll give you two physicists' names who are on opposite ends of the discussion.
Yeah.
One is Henry Margenau, who, when I was at the Yale physics department, he was still there, and he's basically on your side of the argument, and he wrote many books. He's passed now, and I had lots of discussions with him. And on your brother's side of the discussion is a famous Nobel Prize winner, Stephen Weinberg,
Mm-hmm. I know who that is.
and he wrote about exactly the same thing too, but from the other side.
Yeah. Yeah, well, that's pretty interesting philosophical rabbit hole, isn't it?
Yeah.
Yeah.
Okay, well, it's quarter till 20 minutes till. So are we finished?
I'm good.
Yeah.
Thank you.
Thank
Thank you
very
so much for
your
your time and yeah, and you know, your energy.
Yeah.
All right.
Yes.
Well, I love a curious crowd, and you guys had a lot of great questions, and love having physicists in the room. And so I'll send you the video. You guys can put it up, and away we go.
Okay.
Awesome.
Sounds great.
Thank you.
Take care.
Thank
Thanks
you
so
very
much.
much.
Bye.
Yeah.